Okay, so probability, this idea of spin a wheel, what's the probability of getting a one, a two, or a three? A third each, 100% for one of those three. Okay? One, two, and three is often known as the sample space of an event. That's all the possibilities. Okay? That's programming it on a TI-83. You don't have one of those. Actually, the instructions are the same for an 84. Language is the same. The Inspire is significantly different, and I don't know how to do it on there because it's very command based. It feels like it should be, but I couldn't figure it out. There's probably good videos now that YouTube's a big thing, and I mean, I was trying to figure it out in like 2011, but 2008. The design that you currently see, I have a one, I think that came out in 2010 or 11. Yeah, you guys have the CX2. I have a CAS CX1. Doesn't say one, but it's like what changed? I think they upgraded the memory, they upgraded the resolution a bit on the screen. That's about it.
Yeah.
Better battery setup. It can do it for you. So the CAS can do general equations that can solve for any variable, whether it's known or unknown. So you can have four variables in there and it can solve the equation and just get it in x equals form or whatever. Yours cannot do that. It can do calculus in general, but it does terrible with doing the calculus with trig in it. They're correct, but they're off by so many identities that I would never mark them correct because I'd never be able to figure out how you got from A to B. And you probably can't either. Okay, so the probability of an event. This is tossing a coin, and their proportion of heads. Notice that when you've only got one coin toss, it's either one or zero. Two, this one happened to be at 50%. It was just as likely to stay at one. Third one, I guess they got two tails in a row. Another head. Looks like heads. Notice that these proportions are getting closer and closer to 50%. This is an interesting x-axis where they scaled it. You can see the scale getting tighter and tighter. It's kind of a logarithmic type of scale. Um, so, but notice that there is deviation, and down here, even around 100, you're not at 50%. Okay. And then it gets to 50%, and then it goes a little above. And that is randomness. 50% is the long, long, long term. If you're talking millions, we're going to get really close to 50%. But initially, you will get significant variation from that. So, some coin tossers. French naturalist Count Buffon tossed a coin 4,040 times. He got 2,048 heads, or 50.69% for heads. Around 1900, the English statistician heroically tossed a coin 24,000 times. I just laugh at that. He got 12,012 heads, or 0.5005. And while imprisoned by the Germans in World War II, South African mathematician John Carrick tossed a coin 10,000 times, getting 5,067. So I think you should choose heads because it's just slightly higher than 50% on all of these. This is real.
Oh, wow.
This guy heroically tossed a coin 24,000 times. I know. Buffoon. Buffon.
Fun.
Buffon. I can't speak with a French accent. But so yes, all of them came up with very close to 50%. We take the assumption that they are 50-50, and people will tell you, no, it's not. You could land the coin on its edge. Do you know anybody that's ever done that in the history of the world? Not unless you had like a carpet or something. If you're putting it on a table and it's flipping, it's theoretically possible, but it's also possible for you to phase through the wall. So I know how many times you guys have all done that. Yes,
I'm
I think it does. That's why I think all of these three results came out higher heads. Like the slight weight of what's on each side, and it probably depends on the coin. Maybe each particular manufactured coin, but probably the type of coin mostly would have some slight effect on whether it's more heads or more tails. And yes, I've seen a football game where they did a coin flip, but the coin never actually flipped. So they had to redo it. They tossed it in the air and it never flipped. Yep. I'm like, so we call phenomenon random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. So if there's no regular with a large number, it's not random. If there is regularity with a large, the probability of any outcome of a random phenomenon is the proportion of times it would occur in a very long series. 24,000 isn't even a very long series. Okay. I mean, practically speaking, that's a very long series, but when we're thinking we're going to infinity, it's like a limit. Like when I make you do, I've had people calculate E, and it's like 1 over 1 plus 1 over infinity to the infinity. And we use something like 10 million. I'll sometimes have 1,000 and go, this is pretty close, but let's look at what 10 million does. And you could see even with that one with the graph of at 1,000, it was still varying a significant amount enough that I would always choose heads if that variation were going to stay there. But as you keep going, it was kind of going up and down and back and forth. And so thinking about randomness, you must have a long series of independent trials. Do you guys know what independent means?
each problem, one factor.
Yes. Doesn't depend on any other result of another trial or some other random factor, but it would depend on the one before it. The idea of probability is empirical. Computer simulations start with probabilities and imitate random behavior, but they are not truly random. Your calculator does random, and it's a great imitation of random, but it's not truly random. Okay, it uses a formula. Remember when we put the seed in your calculator, you guys can all get the same values. And so I think there's one on the test where it's going to tell you a seed, and then it's going to say pick four numbers, and yours better match with the answer key. Okay? Or it'll tell you you can use the table of random digits. It'll say start at this line. If you're generating your own, you're just going to go like this and point at a line and start there. And if you want to use a table of random digits, if I'm using my calculator, I just don't seed it. But it's very nice. It does follow a formula. All computer random things do. If ones are truly desired to be random, the calculator doesn't care that much. But if you want true randomness, they usually do the seed of some fraction of the second that you initiate the command. Um, Probability has lots of uses, one of which is gambling. That's what it was invented for. In the 1600s. Okay. That was 6.1. That, yep. Well, like I said, this is why we're doing 2 sections in a day. No, it's about twice as long. 6.3 is longer than both of them put together. It's not that bad. I recorded it in like a half hour. Yeah.
We passed 6 seconds.
It's not this. You think you heard very bad things about stats because I took people that were taking pre-calc through it at the A&I pace, and that was a little hard for them.
Use the devil. Use the devil.
I don't think she thought it was quite as bad as Amberly. A day. In a period, yeah, that's about right. But she got an A, I think.
Of course.
I was like, I think all of them got A's. So, um, yeah, it was so yes, you guys are a little more used to the pace. And some of like Jackson's brain just I don't think works in this way. And he didn't want it to work in this way either, was part of it.
You forget. You Stuart gets so.
That's sad. So the stats is a very different way of looking at math. It uses math, but it's like there are some universities that don't have the stats in the math department. They have a own stats department.
Like, oh, that's right.
It gets hard in chapter 10, but
Just one statistic. That's.
it's gonna get weird. You will also find that there will be questions in chapter 5 and 6 that feel harder than, and you'll see the answer and be like, oh, I guess that wasn't that hard. But so probability models. We have a sample space. An event is something occurring, like drawing an ace from a deck of cards, rolling a 6 on the dice, rolling a 7 on a pair of dice. Okay. An event doesn't mean there's only one way it could happen. Like you can to get a 7, you can have a 2 and a 5, or a 1 and a 6. Or a 6 and a 1 is different. Okay. So when you roll dice, for the purpose of probabilities, you have to assume that both dice are different looking. So a 6 and a 1 is different than a 1 and a 6. You guys need a little more time to get those definitions down. A probability model is just some mapping of the probabilities. And I'm gonna do 2 dice in a second. Can I fit these both? Okay, I can fit both of those on the same screen. So here we can see our combinations down here. 1, 1, 1, 2, 1, 3. Notice that 2, 1 is a separate combination. So I'm gonna write the totals next to them. What they add to. It's totally a matrix. It's kind of a probability distribution matrix. So we did some matrices with probabilities, but I mean, this is an outcome distribution matrix, what I'm writing right now. And I'll show you what a probability model would look like here in a second. And they're not particularly hard. And I'm going to do it in non-reduced form. So the lowest outcome we can get is 2. And that is 1 out of a total of 36. 36, if you don't write them all out, is pretty easy to get with 6 times 6. 3, what's the probability of 3? 2 out of 36. So I'm going to write it out as 2 out of 36. Yes, you could probably reduce that to 1/18th, right? What's 4?
3.
Which is 1/12th. 5. 1/9. 5 out of 36. 6 out of 36. 1/6. What about 8? No, it's 5.
It's silly.
Oh, yeah,
Count the 8s. There's 5 of them. It starts going back down. So this whole thing that I'm writing out is a probability model. Does that make sense? I'm not stating the specific ones that make up the 7. I'm just stating its probability. And I'm doing that for every possible outcome in my sample space. Not so bad, is it? So choose a random digit. What's the probability model? Well, each one is 1/10, right? The sample space is all of them. Notice they wrote that in set braces. Flipping a coin and rolling a dice. Your sample space is heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tails 1, etc. That makes sense? You can do this with a tree diagram. If I want to do this, and this is going to lead into something tomorrow, so I'm going to write it out here. No. So this one, what I'm doing here is I'm writing the probability on each one. I should probably do this as fractions. It's a little bit easier to multiply. 1/12. So to get the probability of anything down the chain, you multiply the probabilities as you go. Okay, on a tree. The last example tomorrow is a decision analysis on whether or not to have a kidney transplant. And there are some formulas for calculating each of the ends. The tree diagram is way easier. And so you just write the probability of each branch on the tree, and then to get to the end of it, you just multiply it. I could add more branches here, and then I just multiply this times 1/2 again, so 1/24th. Okay. You do not have to go the same number of branches for each thing either. Just because you've got extra branches up on this one doesn't mean you have to have them down here. Okay. When you draw a tree diagram, it is important to draw your things wide enough initially that you still have space later on to make stuff fit. Multiplication principle. The number of ways something can be done is A times B. With the dice, there were 6 for each dice, so 6 times 6. Or 6 for each die. Or each 6-sided number cube. If you ever see that, that just means a dice. So flip a coin 4 times. You can either get 0 heads, 1 head, 2, 3, or 4. Make sure not to forget the 0. We'll often identify it as the number of either heads or the number of tails. Okay. Not 2 heads, 2 tails. We'll just call it 2 heads. 3 heads instead of saying 3 heads, 1 tails. Often the easiest way to figure out the probabilities is what's called the brute force method, which basically means list out all the possibilities. And I don't feel like writing it, so you can see here that 0 heads is tails, 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 tails. 1 heads is heads, tails, tails, tails. One way of thinking of this is there's 4 places to put I am going to have 16 possibilities. I've got 4 flips of a coin. 2 options for each one. I multiply them. There is one way to get no heads. There is 4 ways I can put the heads in any of the 4 positions. To get 3 heads, I can put the 1 tails in any of the 4 positions. So the brute force method, honestly, with this is probably easiest. Usually I start with a system, I do something like this, and then I just move the heads down like they did. And then my next one, now I'm going to start with tails because I've done all possibilities starting with heads. Start with tails, I'll do 2 heads, move the heads down essentially do it in some sort of sequence so you don't miss things. The other way to figure this out, there's 6. You could also I've got 16 total, I've used 10 of them. That leaves me with 6 for this one. That would be harder if we did 5. Although I believe 2 and 3 heads and 5 would be the same. My sample space is 0, 1, 2, 3, or 4 heads. Generating a random decimal between 0 and 1. Each thing is equally likely. Generally, you put a limit on how many decimal places you're going to do, but what you'll do is you'll generate a random number and you'll pick this range corresponds with something. I prefer to just use random integers. It's important to think about when random events, whether you have replacement or without replacement. If I draw a card from a deck and then I put it back in, I've replaced it. My probability of getting any card then becomes 1 in 52. And it continues to be 1 in 52 if I keep replacing it. However, if I draw a card and don't replace it, I've got 1 in 52. Let's say I want to draw an ace. I've got 1 in 52 or 4 in 52. And then the next time, if I drew an ace, I have 3 in 51. If I didn't draw an ace, I have 4 in 51. Okay. Make sure to discount those things. If you pulled something out, you have to consider it pulled out. That showed up in that first problem on that sample test I gave you at the beginning of last year. Okay, probability rules. And I'm just going to show you 5 of them in notation. So the notation is at the beginning of this. And it'll be reviewed in your video tomorrow I'll give you more detail today. Okay. Probability rule number 1. We notate probability of an event as P parentheses A, kind of like function notation. Probability of any event, you could say P of ace. Okay? I can write it out in words, or I can just say event A, and I must specify what A means. Okay? It's always a number between and inclusive between 0 and 1. Okay, that's between 0% and 100%. Yeah. The probability of any event is always something between with including 0 and 1. The probability that tomorrow's my 20th birthday is 0. The probability that tomorrow is January 22nd, 2026 is 100%.
Or is- maybe that there might have been something. Before the year 0, because there was like these kings or something, and they just wanted. I think it was something about like wanting it to be the year 1000 or something that made them seem more powerful. I don't know. There's like a whole 300-year period where historians like can't find very much. Interesting.
Interesting. I have not heard of that, but that's. But by when I say 2026, I'm using the dates of the Gregorian calendar, I think. Well, it's only the dates on the Gregorian calendar we believe are accurate, and it's what we use. Our our solstices would be off. Um, does that make sense for the first probability rule? Second one, the probability of the sample space, all possible events, is 1. The sample space would be probability that everything that's possible they all happen. The complement rule. Probability of a complement. The complement means not the event. So it's 1 minus the probability the event happens. Which, do these all make sense so far? And like, there is not much logic so far in this. You haven't had to do much, but hopefully it is pretty straightforward. So, the addition rule, if A and B are disjoint. Another word that we'll see for disjoint is mutually exclusive, and they mean the same thing. Meaning there is no overlap. If A occurs, B does not. You cannot get both an A and a B in second trimester of A&I for a final grade. You can get them for individual grades, right? But you cannot get a final grade that is both an A and a B at this school. Some universities used to have a grade AB, which was like A minus B plus. I don't know. That's why I think it's mostly gone. Um, Lots of events have overlap. You can be both female and a senior in high school. You can be both male and a senior in high school. You can be male and a junior in high school. Okay. You can be male and not in high school. That's yes. I'm like, I suppose at some schools you could be teacher and principal. The school's small enough. Um, you can see this.
Yeah.
You should make a movie about it.
Yeah.
And then you have the multiplication rule. So for this, if they're disjoint, so A or B, so if it's either A or B, you just add them together. That makes sense, right? They're separate things. If they're not, there's a rule for it we'll get into tomorrow. If they are independent, this rule works both ways, hint, hint for your test. If this is true, then so this is an if and only if case. If two events are independent, P of A and B is P of A times P of B. If P of A times B equals P of A and B, then they are independent. If P of A times B does not equal P of A and B, they are not independent. It doesn't matter if they seem like they are. Okay? So if this rule is not true, this is a bidirectional, biconditional.
Okay, who's the last one about only?
If P and A does not equal P of A and B, then they are not independent. It does not matter if they seem independent. So I wish they would have given this as a biconditional. A and B are independent if and only if P of A and B equals P of A times P of B. Yeah, biconditionals. You're supposed to learn that in geometry. I'm not sure how many of you really did. Elise did. Like, I know I taught that. So it means it has to work both ways. It means either one of them can be the if. So those are my general probability rules. There's the shortened version. I don't know why they didn't. I guess they wrote it out or there. Here, these are disjoint events. You guys are familiar with Venn diagrams, correct? Um, this is A and A complement in a Venn diagram. They just didn't want to draw a nice straight line down the middle because it doesn't make it sense sometimes. So this is the marital status of young women, 25 to 34. Okay, we have never married, married, widowed, divorced. So, what's the probability of not married? That's 1 minus married. That's easier, probably. You could also add up never married, widowed, divorced, since you have all that data. But this complement rule is very nice and powerful. Did I ever do the birthday problem with any of you guys in the class? I think I did for Elisa's class. Yeah. How many people you need in a room before the birth probability is more than 50% that two people share a birthday? Anybody remember? Too high. Yes. It's 23. Did you actually remember that? Or were you just guessing? I know. I was like, wait a second. It's 23. You calculate that. It's pretty easy to calculate that people don't share a birthday because the second person not sharing is 364 out of 365. Third person not 363 out of 365. And you just multiply it. Usually the probability that someone does share is 1 minus the probability that no one shares. And at 23 people, you cross the 50% barrier. A group of 30 is like 70 some percent. Okay, probabilities of rolling a dice. So they're saying the probability of rolling a 5, 4 out of 36 or 0.111, and they've shown all the possibilities. I think just making the table is often easier. Benford's law. This is a weird law, but this is true of real data. And they will actually test against this to see if, something is cooking their books. You guys know what that is?
Is Benford's law where like ones and twos are more likely to appear?
As the first piece of a data set. So the probability that your first digit is 1 is essentially 30%. Do you guys understand why this would be real? So if we're talking incomes, this doesn't really apply that well in the thousands range because 10,000 doesn't work real well. But a lot more people make in the 100,000s than in the 500,000s. And there's much higher percentage once you cross the upper 100,000s, there's much higher percentage that make in the 1 millions than make in the 5 millions. And then there's a much higher percentage that make in the 10 millions than the 50 millions. Okay. And it has something to do with the multiplication, but doubling 500,000 is a million. Doubling 900,000 is 1.8 million. Those both start with a 1. Okay. Doubling 1.8 million goes straight to 3.6. Okay. There's a lot of this kind of multiplication thing, and that's kind of why this is. So this is page 345. It'll usually be shown, but this is going to show up in several homework problems. You do not have to generate this. This is, I believe, an observational law. Okay, I do not believe this is proven, but this is just large collections of data. You cannot determine somebody cooked their books because their data doesn't fit Benford's law, but it gives you a good indication if you're the IRS as to who to look into. Okay. Now, I think if you have somebody good cooking your books, they will be aware of Benford's law. Okay. There might be some secondary things, but applying the probability laws, probability of A is first digit is 1, B is first digit is 6 or greater. First digit is 1.301. We just looked it up in the table. 6 or greater. There is no shortcut with complements here because you don't know 5 or less. So you just add the 4 together. And 6 or greater actually has less probability than 1. But it does have higher probability than 2. 1 or 6 or greater, you just add those two together. Not 1, so 2 through 9, you just do 1 minus 1. So 30% chance that it's a 1, essentially, and a 70% chance that it's not a 1. Versus uniform would be a 10% chance that there's a 1 and a 90% chance that it's not a 1. Well, no. It'd be a 11% chance that it's a 1 and an 89% chance because your first digit cannot be a 0. So B or C. Oh, they added event C, which is C is the first digit is odd. B or C, you have to do 1, 3, 5, and then 6, 7, 8, 9, because 6 through 9 was in event B. That makes sense? And again, it's probably easiest to just add them up. They would all be, so if you did 6 through 9, if they're equally likely, you'd get 44% as opposed to 22%. think this, nope. Independence. So we talked about them, you have to multiply them. In the Venn diagram, P of A and B is this overlapping region. You guys are all comfortable with that. Okay, and I did show you this rule before. Independent or not, because a coin has no memory, most coin tossers cannot influence the fall of a coin. It is safe to assume that successive coin tossers are independent. Um, so you can assign each one as one half. On the other hand, successive cards dealt in a deck are not independent. And we talked about that, right? You're talking, and it's different depending on which one is dealt. Um, you guys know Gregor Mendel? Yeah, P plants and dominant and recessive genes, Punnett square. You can do the Punnett square with probability rules. Each one in the Punnett square was a quarter in the long run. Okay, this one. Transatlantic telephone cables. The first successful transatlantic telephone cable was laid in 1866. Or the first telegraph cable, 1866. The first telephone cable did not appear till 1956. Okay, the barrier was designing repeaters. Amplifiers are needed to boost the signal, could operate for years at the bottom of the sea. The first cable had 52 repeaters. The copper cable laid in 1983 had, and retired in 1994, had 662 repeaters. The first fiber optic cable was laid in 1988 and had 109 repeaters. Now we have tons of miles of fiber optic under the sea. Repeaters are very reliable. Suppose we have a repeater with probability of 0.999, 99.9%, that each repeater will work for 25 years without failure. So, what's the probability that your cable lasts 25 years? Well, with 10 repeaters, it's 0.99 to the 10th. But with 662 repeaters, it's 0.99 to the 662nd, which is only about 51%. There's a 48.4% failure rate, chance of that it won't last 25 years when you have that many repeaters. Even though each one failing individually was so unlikely. Does that make sense? And again, using that complement rule becomes very powerful. This one, AIDS testing. This is probably important to know as a human being. Screening large number of blood samples for HIV, the virus that causes AIDS, uses an enzyme immunoassay EIA test that detects antibodies for the virus. Samples that test positive are retested using a more accurate Western blots test. Probably it's more expensive, so they don't just start with it. Applied to people that have no HIV, EIA has a probability of 0.006 of producing a false positive. That's not very good, is it? If 140 employees at a medical clinic are tested and all 140 are HIV free, what is the probability of at least one false positive? Well, it's 1 minus the probability of no false positives. And if you have someone with HIV in your health clinic, it becomes a lot more scary because the transmission rate in healthcare becomes a lot higher, right? Just because of the ease of. So you take 0.994, so it's only 0.06, but we got to use the complement. So 0.994 is the probability of no positives. So that's they all come out correct. You end up with a 56 point, basically a 57% chance that you're going to have somebody come back with a positive. Not likely that it'll be you, but likely that someone will. More likely than not, even though the test individually was very low. Okay? Any questions? Okay, go ahead and work on some stats problems. If